This is a question on how we classify waves, and the answer to this question is D. The difference between a transverse and a longitudinal wave is in how the particle motion is as compared to how the wave travels. So for transverse wave, the particles actually vibrate perpendicularly to the direction of the wave. And for longitudinal wave, the particles actually vibrate and move parallel to how the wave travels. Now we will start with the distractors, which is option B. The medium at which the wave travels is not considered a difference between the two types of waves, because both types of waves can travel through different mediums. And when a wave travels through a different medium, the velocity and the speed of the wave will therefore change, and that's the reason why C, the speed of the wave, is also not considered a difference between the different types of waves. Now collectively, based on the wave equation, the wavelength of a wave is determined based on the speed of the wave and also the frequency of the wave. So both longitudinal waves and transverse wave will have a corresponding value for wavelength, and therefore A is also not considered a difference between a transverse wave and a longitudinal wave. This question is about longitudinal waves, and the answer to this question is D. Statement D is not correct, meaning that a longitudinal wave, or in fact any waves, transverse or longitudinal waves, they do not transfer the particles from the source to the other to other places. The particles actually just move about a fixed position, whether is it a transverse or longitudinal wave. So D is therefore not a correct statement. Now, for option C, ultrasound waves are sound waves at very high frequency, so therefore they are longitudinal waves. Is a correct statement. Option B is a correct statement also, because that is how we define a longitudinal wave. And option A, longitudinal waves or transverse waves can undergo reflection, or actually in fact also refraction, depending of the wave. So you'll practice on this in one of the questions later on in the SQ. This is a question that is pretty tough, and I have thought of your technique in the class to solve this question easily. So let's apply that technique that you have learned. The answer to this question is B. Alright, and let's take a look at how we get this answer. So we always look at the particles at the crest or the trough position first, because it's pretty easy to determine how these particles will move next. Now, since particle P is at the trough position, it's already at the bottommost position. So in the next instant, it will have to move upwards. And you are tempted to write the answer for P to be upwards, giving A as the answer. But if you think about it, that is happening in the next instance. In the next instance, particle P must move upwards. The question asks you what is happening to these particles at this current instant. So it's better to describe particle P as currently stationary, not moving, and that's why B is a better answer. Now, the next step to solving this question is to look at how the wave travels. The wave is moving towards the right. This must mean that the crest and the troughs of the wave, they are all moving towards the right. So if you track this trough position of the wave, we will notice that this trough position is it will be moving towards the right, and therefore particle Q in the next instant, it must travel downwards to be at the trough position. So this is the reason how we concluded that Q must therefore be moving downwards. Now, to get the direction of particle R, we can repeat the same analysis again. So meaning that we can look at the crest here and reason that the crest is moving towards the right, and particle R must therefore move upwards to take the position of the crest in the next instant. So this will get us the answer R to be moving upwards. However, there's another shortcut to getting this answer. We can argue that both particle Q and R, they are half a wavelength away, and therefore these two particles are completely out of phase with each other. So this means that particle R must be moving in the opposite direction as compared to particle Q. For this question, the answer to this question is B. B shows the wavefronts of this wave. Now, you must know the definition for wavefront is this imaginary line on a wave that connects all the points of the wave that are in phase. And if you recall what is in phase, it means that the particles of that wave, if they are in phase, they are moving in the same direction, they have the same speed, and they are of the same displacement away from the rest position. So exactly what line B shows. Now, line A actually shows the amplitude of the wave, which is the maximum displacement of the particles away from the rest position. Line C, the distance C, actually represents the length of one cycle of a wave, which is otherwise known as the wavelength. And option D has no special name. Option D is just the surface of a wave. There are two graphs in the study of waves that we use to analyze our waveform. And one of it is displacement distance graph. The other one is a displacement time graph. Each of these graphs carries different information that we can pull out from the graph. The answer to this question is D. So if we look at the displacement distance graph, we will notice that the length B over here shows the length of one complete cycle from here all the way to here. So this is otherwise known as the wavelength. And amplitude can be gotten from this distance A, which is from the rest position, what is the maximum displacement of the particle away from the rest position. Same thing, the amplitude can be gotten from a displacement time graph in a similar way. And this on the horizontal axis, the interval between or for one complete cycle is known as the period. Alright, these questions, the answer to this question is A, and we will need to determine how will the particle move in the next instance. So first we note that the wave is moving towards the right, and therefore all the crests and all the troughs will correspondingly also move towards the right as the wave travels. This therefore must mean that particle P must move upwards so that particle P can become the crest later on in time to come. So after deciding and concluding that the particle P will move upwards, we next note that in one complete cycle, particle P will be found back at the original position, and this takes the time interval of one period. So we can then break up this movement into 4 segments. It takes 1/4 of a period for the particle to move up here, another 1/4 of a period for the particle to move down here, and the third quarter of a period the particle will move down to here, and finally in the last quarter of the period the particle will move up and back to its original position. So after a quarter of a period, particle P will be found right at the top, and that corresponds to what graph A shows. Particle P is found at the top. This is a very interesting question to assess us on our understanding of displacement distance graph. So the answer to this question is A. A is the correct statement, and the reason for that is because particles K and M, they are a wavelength apart from each other. So particles that is a wavelength apart from each other, they are in phase, and therefore they are moving in the same direction, they have the same speed, and they are the same distance away from the rest position, which is 0. Now option B is not a correct statement, because on the horizontal axis here we are plotting distance. So the distance between particle K and particle M is 4 cm. 4 cm is actually the wavelength instead of the time interval, which is called period. Option C, we have to repeat the technique to determine how the particles are moving, and we noted that the particles or the wave is moving towards the right. This means that the crest position here will be moving towards the right along with the wave. This means that for particle L, in time to come, it will have to move up so as to take over the crest position, and that's the reason why option C is not correct. Lastly, for option D, particles N and L, they are found at the same distance away from the rest position. Now, as we all know, particles at the crest and at the trough positions, they are momentarily at rest with zero kinetic energy. So they have the lowest amount of energy inside them. In contrast, particles at the rest position, over here and over here, these particles are moving with the fastest speed, having the highest kinetic energy. So when particles are away from the rest position, for example L and N, they will have the same amount of energy because they are found at the same displacement away from the rest position. This is a question on the wave equation, and also how it assesses us on how well we understand what frequency and what wavelength means. So the answer to this question is C, and when we see the phrase 20 vibrations every second, it tells us that the frequency is 20 Hertz. When we see that the spacing of the ripples from one crest to the next crest is 3 cm, this tells us that the wavelength of the wave is 3 cm, and therefore we can plug these values into the wave equation to get the answer. This is a question of wave equation, and the answer to this question is C. We can read from the question that the velocity is given to be 5 meters per second and the frequency is 25 Hertz. So with these two data, we can use the wave equation to find the wavelength of this wave, which is 0.2 meters. This means that one complete cycle of this wave, the length of one complete cycle is 0.2 meters. In 1.4 meters, we can fit 7 times of this 0.2 meters, and therefore the answer is we can find 7 complete waves within a total length of 1.4 meters. Question 10 is a question on wave equation, and the answer to this question is D. We noted that the velocity of the wave is 1400 meters per second. Always convert the quantities to SI units. and the wavelength is as shown. Again, always convert it to SI units. So plugging in these values into the wave equation, we can therefore get a value for our frequency of the wave. This is a very unique question on wave speed, and the answer to this question is B. So how do we get 0.8 meter per second as the speed of the wave? First, we must recognize that all these circular lines, these are wave fronts, and wave front to wave front, the distance is actually one wavelength. So from P to Q, we are looking at 1, 2, 3, and 4. We are looking at 4 wavelengths. That is the distance between P and Q. And this is given to us as 8 meters because one wavelength is 2 meters over here. So now we have the distance from P to Q to be 8 meters, and the timing taken from P to Q, for the wave to travel from P to Q, is 10 seconds. And therefore, what remains to be done is simply just use distance divided by time to get the speed of the wave. This is a very important question on our understanding of frequency, wavelength, and speed. And the answer to this question is C. Now, in equation form, the wave equation has these 3 quantities, but it does not tell us which of these quantities is more fundamental. So we must know that the frequency of a wave is the most fundamental. It doesn't depend on wavelength or velocity. In fact, a frequency determines the wavelength of the wave later on. So frequency is very fundamental because it originates from the source of the vibration of the wave. And once the source vibrates a medium, the frequency is already predetermined and set. And the frequency of the wave will therefore sort of follow the wave as the wave transfers energy to other places. So a frequency of a wave will not change as the wave travels because it was determined by the source of the wave. Now, speed of the wave depends solely on the medium at which the wave travels. You have learned this in the chapter of light. When light rays travel to an optically denser medium, it slows down. So similar to these waves, water waves for example, when they travel from shallow into deep water, they will speed up. This is something that you must memorize. And the speed of the wave depends only on the medium. It does not depend on the frequency, and it does not depend on the wavelength. Lastly, wavelength of the wave is always the consequence. So based on the wave equation, the wavelength of the wave is determined as a consequence from the frequency of the source plus the speed of the wave due to the medium. So together, the frequency and the speed of the wave will therefore determine what is the wavelength of the wave as it travels through the medium. This is a question on the wave equation and also on the effect of the wave from deeper to shallow waters. So the answer to this question is A, and this is how we reason out the answer. Now, we first look at the deeper region. We are given that the speed of the wave in the deeper region is 20 meters per second, and this distance over here is 16 cm. So with velocity of the wave known and the wavelength of the wave over here, we can then determine what is the frequency of the wave. Now, the wavelength can be gotten because these are wave fronts that we see, And we know that from wavefront to wavefront, the distance is actually one wavelength. So over here you can see there are two wavelengths that takes up 16 centimeters. So one wavelength is just 8 centimeters. Now, once we have determined frequency to be 250 Hz, we must know that frequency of a wave do not change as the wave travels. And the reason for that is because the frequency of the wave is determined by the source of the vibration, and once the wave starts with that particular frequency, the frequency will carry on throughout the whole waves without changing. So when the water waves gets into the shallower region, the frequency remains the same as 250 Hz, and given that the speed now slows down to 8 meters per second, we can again use the wave equation to figure out what is the wavelength of the wave in the shallower region. So we got that to be 3.2 centimeters. So in this question, you can see a transverse wave obtained by oscillating the ball in a vertical direction. We noted that the direction of the wave is moving towards the right. In part A, you are to determine the amplitude of the wave. So the arrow drawn over here shows double the amplitude from a crest to a trough position. So when you're measuring the distance, please measure it to scale. You might get a different answer based on the printout, but as long as you recognize that this distance over here, this height over here is double the amplitude, you should be able to get the correct answer. In part B, this distance between a trough to a trough, or you can also use the distance between a crest to a crest, or the distance between this rest position to the second rest position, skipping one rest position. All these are distances that represents the wavelength of the wave. In part 2, if you are given that the ball oscillates 40 times in 60 seconds, to convert this into a frequency, which is the number of oscillations in 1 second, we can just simply divide 40 times across 60 seconds by 60. So if you use 40 over 60, you will be able to get the number of vibrations in 1 second. And this is how we can obtain the frequency of the wave. What remains to be done is to use a wave equation and to plug in the values for frequency and wavelength to get the wave speed. Finally, in part C, this is how we can describe the motion of the particles in a transverse wave. The particles in a transverse wave move perpendicularly to how the wave travels. So in this scenario, since the wave is moving towards the right, the particles are moving in a up-down motion. This is a long question on waves. So in part A, we can determine the wavelength of the wave if we can identify the correct position of the waves to measure from. So this is an example of how we can determine the wavelength of the wave. From one rest position, we skip a rest position and we go on to the next rest position. These two particles over here and here are in phase, and the distance between two particles in phase is the wavelength. We can also easily determine this wavelength by measuring the distance from the crest here to the crest over here, or the trough here to the trough over here. So the answer to this question is 0.4 meters being the wavelength. In part B, learn to provide the necessary details in the description of how the particles move in a wave. So particle B will move down in the next instance until it reaches the maximum displacement which is over here. And after that, this particle B will then move upwards crossing the rest position to the maximum positive displacement before going downwards to the rest position, and throughout it will pass by B. So in your description, ensure that because we start at position over here, one full cycle means that the particles will move down, move up, and move back down to B, and this will represent one complete cycle. Now, we can also determine how why the particle B will move downwards if you use one of the techniques that I taught you all previously. That if you look at this trough, the trough will move in the direction of the wave, which is towards the right. So this means that the trough will be moving towards the right, and this point will be where the trough is in time to come later on. This must mean that the particles here must be moving downwards to take over the trough position in time to come later on. And this is how we can determine that particles along this stretch of the wave must be moving downwards in time to come. And this is how we can get B will move down in the next instance. Now in part C, mark a point where the particle has the same speed as A but moving in the opposite direction. This means that we are choosing particles that is out of phase, completely out of phase with particle A, and therefore we can note that these two particles over here and over here, these two particles will be half a wavelength away, and these are completely out of phase particles. Just remember that particles that are in phase with each other, they are one wavelength distance away, and therefore for particles to be completely out of phase, these are the particles that is half a wavelength away from the particle. So over here you can see half a wavelength and half a wavelength. That's why these two particles are particles that are at the same position, but they are moving in opposite direction compared to A. In part D is a simple question to calculate the distance moved by the wave if you just use speed times time to get 0.2 meters. And in D part 2, where will the wave be in 0.1 seconds? So we noted that in 0.1 seconds the wave would have travelled towards the right by 0.2 meters as shown over here. This means that all my crest, all my trough will all move towards the right by 0.2 meters. So here I mark the new position of the trough after it moved rightwards for 0.2 meters. And we can repeat this analysis for the trough and for the crest, and for all the rest position. Basically we will get coordinates like this if we do it slowly and carefully, and this will therefore be the graph or the graph of the wave after 0.1 seconds. This is a long question on waves, and in part A, a wavefront is an imaginary line on a wave that joins all the adjacent points that are in phase. In B part 1, we have to take some measurements to figure out what is the frequency and what is the speed of the wave, and therefore we notice that from P to Q there are 3 cycles. So this is the first cycle, then second, and the third cycle, and this takes place in 1.2 seconds. This therefore means that the 3 cycles happening within 1.2 seconds, every cycle will only take up 0.4 seconds, and this is the period of the wave. And to convert period to frequency, we just use the formula F equals to 1 over T to get 2.5 Hertz. Now, speed of the wave can be gotten from the wave equation, but we still need data on the wavelengths of the wave. So therefore we can actually obtain the wavelength from this measurement over here. This is one wavefront to a second wavefront, and therefore this is the distance of one complete cycle, which is the wavelength, and this is 1.2 cm. and that's how we can obtain the speed of the wave using the wave equation. Now, when you sketch out the graph for C, the displacement distance graph, there are a few things to check. First, check that you have represented the amplitude of the wave to be 6 cm. So over here, all this position should be at 6 cm, and over here, this maximum displacement is negative 6 cm. Okay, next, notice that when we start with a crest, because P represents a wavefront, so let's take it to be a crest. One complete cycle, the wavelength is 1.2 cm. So from a crest to a crest, this distance should be 1.2 cm. And the troughs will happen at half a cycle away, which is over here, and this should be 0.6 cm away. So these are the things that you should check for your displacement distance graph of this wave. Now, part C is a very interesting question about refraction in water wave. So I'll teach you a technique on how we can solve this. So for waves, we can see that there are wave fronts here, okay, and we draw an arrow here to represent the direction of the wave. Notice that this arrow is perpendicular to all the wave fronts, and this arrow also looks very similar to a light ray. So second thing, we must know and memorize this, that water wave slows down when it goes to a more shallow region. Okay, so when the wave slows down, for example, when a light ray slows down, the light ray actually bends towards the normal, as what you have learned in the chapter on light. Same thing goes here. When the water wave slows down, as it changes medium to a shallower medium, the water wave will bend towards the normal. So by right, the water wave should go straight, but because it slows down, I draw the normal and indicated that the water wave actually bend towards the normal. So this is the blue arrow that I just reconstructed. And lastly, I will then recreate all the wave fronts. We must carry on the wave front, join the wave fronts from all these points over here, and all my wave fronts in orange starts from these points. And these wave fronts are again perpendicular to the direction of motion of the wave, which is what I mentioned just now. So there you go. This will be the complete diagram on how to draw a refraction diagram for water waves. Do learn this and try it out yourself also. Now, once we have the drawing, we can actually solve part 2 in 2 different ways. Without a drawing, we can use the wave equation to argue that the wavelength of a wave, when the speed of the wave slows down and frequency doesn't change, the wavelength of the wave in deeper water will be larger. So when it goes to a shallower water, the wavelength will be smaller because of the slower speed. Now, again, a reminder that frequency of the wave do not change whether it's in the deep water or in the shallow water, because the frequency is determined by the source of the wave. With the diagram here, we can see visibly that the wavelength, which is here in the deeper water, has now decreased in the shallower water, telling us that the wavelength has already decreased when it goes into a shallower water. So there are 2 ways to solve for C part 2.